Good evening. Every molecule possesses certain energy, and these energies are equally distributed among different degrees of freedom within the molecule. A molecule may possess vibration degrees of freedom, rotation degrees of freedom, and translation degrees of freedom. These are due to vibration motion, rotation motion, and translation motion. Here we are dealing with vibration modes. For a linear molecule, there will be 3n minus 5 vibrational degrees of freedom, where n is a number of atoms. And in the case of a non-linear molecule, the number of vibration degrees of freedom will be 3n minus 6. If we consider a diatomic molecule, that is molecule with only 2 atoms, then there is only one possible vibration. It can be either stretching vibration or compression. If we consider a polyatomic molecule, that is molecule having more number of atoms, then it will be having n minus 1 stretching modes of vibration in the case of molecule having n minus 1 bonds. That is, it will be having the same number of stretching modes of vibration as well as the number of bonds. And these vibration transitions are mainly caused by IR radiation. And if we have high resolution spectra, the rotation and vibration bands can be distinctly observed. If we consider carbon dioxide, it is a linear center-of-symmetric molecule. Center-of-symmetric molecule means it is having a center of symmetry. If we move on either direction from carbon, we will reach same kind of oxygen atom. Such molecules are known as center of symmetric molecule. It is a linear molecule as well. So, to find the degree of freedom, vibration degrees of freedom, we have to use the equation 3n minus 5, where n is the number of atoms, and if we put the number of atoms in carbon dioxide, which is equal to 3 in the equation, we will get 3 into 3 minus 5, that is 4. So, we can conclude there are 4 vibration degrees of freedom. And if we resolve these 4 vibration degrees of freedom, we can find that one is symmetric stretching vibration, which occurs at a frequency of 1388 cm inverse, and the other is asymmetric stretching vibration, which occurs at 2349 cm inverse, and another is 2 degenerate vibration. Degenerate vibration means this vibration occurs at same energy. It is at 667 centimeter inverse. These are symmetric stretching vibration, and the degenerate bending modes of vibration are IR active, whereas symmetric stretching vibration is IR inactive. So, if we take the IR spectrum of carbon dioxide, we cannot see the symmetric stretching vibration at 1388 centimeter inverse, whereas the asymmetric stretching vibration at 2349 centimeter inverse, and the degenerate vibration due to the perpendicular bending vibration of the carbon dioxide molecule can be observed. So, we can conclude that in an IR spectrum of carbon dioxide, there will be only 2 bands, one denoting the asymmetric stretching vibration and other denoting the degenerate vibration. The degenerate vibration is bending modes of vibration. Always it is bending vibration will be in the lesser frequency region compared to symmetric stretching and asymmetric stretching vibration. And when comparing symmetric and asymmetric stretching vibration, asymmetric stretching vibration requires higher energy compared to symmetric stretching vibration. Selection rules for IR activity. For molecules, to show IR activity, there should be certain conditions. And one of the conditions is there must be dipole moment change during vibration. If the compression or the elongation takes place along the same axis on either direction in the same way, then there will not be a net dipole moment. So, in the case of symmetric stretching, the dipole moment is 0 and it is IR inactive. Dipole moment change can occur in 2 ways. Either it can occur parallel to the symmetric axis, or perpendicular to the symmetric axis. If it is occurring parallel to the symmetric axis, it is known as parallel vibration, whereas if it is occurring in